Hello, I'm Richard Hooper and this is SatTV. Now I'm pleased to be joined by Antoine Halff, Chief Analyst and Co-Founder at Kayrros. Thank you for joining me today, Antoine.
Thanks for having me.
Now, tell me a little bit about Kayrros and the reason behind the company.
Kayrros is an environmental intelligence company. We could call it a digital MRV company. Basically, we use AI and ML and we process satellite imaging. We use some other data sources as well. And the idea is to create transparency, the transparency, the data, the information that we need to achieve our climate goals. So we created the company in 2016. So just a few months after COP21, the Paris Agreement. It was quite clear to us at the time that the Paris Agreement set very wonderful ambitions and the right targets, the right policy goals, but that the world did not have the means to deliver on these goals for lack of measurement capacity. So I was at the time at the International Energy Agency, which is a great organization, but I realized that even there, to monitor the energy space, energy supply chains, we often had to make educated guesses, and there was a lot of gaps in our knowledge of a very mature market at the time. But when it came to climate issues, to reducing our greenhouse gas footprint, to managing climate risks, there we were in a complete desert, and there was a need for measurements, for monitoring, for transparency. But we also felt that we could achieve this transparency by tapping into the proliferation of new data sources that became available, that were becoming available at the time. Satellite imaging was one of the sources we thought of at the time. We thought of, scraping websites around the world, government websites, private websites. There's a lot of information out there. We thought of tapping into social media and posts and extracting information from that. Geolocation devices and so on. Satellites was one tool in the toolbox, not necessarily what we thought would hit the jackpot at the time, but very quickly it turned out that we managed to deliver, to gain insights into the physical world and particularly the world of emissions, using satellite imaging, processing satellite images with AI, machine learning, that exceeded our expectations very, very quickly. So that was the idea. The world needed measurements to manage the climate. We did not have those measurements available, but we had the means to make them available. And that's what we set out to do. So we were a set of 5 co-founders, 2 from the energy industry. Our president, Antoine Halff, came from Schlumberger. I came from the IEA, the International Energy Agency, and our co-founders were all mathematicians, artificial intelligence experts, satellite experts, and so on.
Now, you mentioned satellite, and that's what you tapped into. But why, as a technology, is it so important to monitoring our planet?
Well, satellites give us a lot of information, and there's a tsunami of satellite data flooding the planet every day. The main issue with exploiting this wellspring of information is processing capacity. So when we started, there weren't quite as many satellites as today. The fleet has dramatically expanded, but there were satellites, and we had some information about some of the things we started looking at, but they were very isolated, punctual, few and far between. What we did is deliver the capacity to process satellite images at scale, do it massively, process tens of terabytes of data every day, and run raw images through our algorithms and extract signals from that. And then when we started doing that, we realized that we could extract information, for example, about methane from a sensor that had been designed to monitor methane. And we extracted many more, we identified many more super emitter events than we ever knew existed at the time. But we also realized that we could extract methane information from satellite data coming from sensors that had not been designed initially specifically to monitor methane. So we basically realized that by pushing the envelope, by pushing the frontier of image processing, we could really augment the volume and the quality of information that we could collect from satellites. We actually started with crude oil inventories because this is something for which the business case was very well established. There was a clear need for information on some markets that were increasingly accounting for a growing share of the global crude market, but were not covered by government statistics in a way that was appropriate. So we set out to do that, and we could calibrate and benchmark and verify the quality of our methods by comparing it with some of the better government statistics out there. But then we expanded into methane, and then we broadened the field, and we started looking at ways of monitoring carbon emissions in quasi real time with global coverage and a lot of granularity. And then we looked into vegetation, forestry, biomass, carbon embedded in vegetation, and the list goes on. So there's just a huge wealth of information out there from satellites. Most of the instruments that we use are government owned, so the cost of acquisition for us is zero, and all the work that we provide is really on the processing side, and all the expenses all the cost of delivering these data really come from the processing side, not from the hardware side. We also use commercial satellites as needed, but there's just a tremendous amount of information, particularly from the Copernicus constellation of the European Space Agency, which had a lot of foresight and launched climate observing satellites very early on. So we've benefited from this incredible wealth of information, and then we've added many other fleets. We use Landsat 8, Landsat 9 from NASA, many satellites from government agencies, and so on.
How do you get the accuracy when monitoring methane emissions? Because let's reference a report from Stanford, which was glowing about the accuracy.
Yeah, it's a good question, because a lot of the methane emissions that we detect from space basically are not detected by any other means, and very often cannot be detected. So the question is, how can we prove that the data are right? There's a few different ways, but you mentioned the Stanford study. So there's a group of experts at Stanford University that set out to basically test the accuracy of our data and the data provided by other teams. And what they did is they set out to do controlled releases of methane, blind releases. And then they tasked a number of groups, including us, to identify the releases and to measure them and to pinpoint them. So that's what we did. We actually, before that, there's different types of releases and different causes for methane emissions. It ranges all the way from the small leaks that are ongoing but very small, can add up to a lot of methane but are very tiny, cannot be seen from space, to massive events that may be very short-lived but may in a couple of hours release as much greenhouse gas as the equivalent of tens of thousands of cars running for an entire year. So depending on what type of releases, they can be sometimes measured at the source. If, for example, pipeline companies do maintenance on the pipeline and decide to isolate a segment of the pipeline, release the gas, they typically know exactly how much gas they're releasing when it's a deliberate venting decision. So we've sometimes compared our detections of large emissions coming from pipelines with what the pipeline operators had to say, and and this might come as a surprise, but at the time we picked up many events on a couple of Gazprom pipelines bringing Russian gas to Europe, and we turned to Gazprom and we called them and we said we detected this massive release on your pipeline at this at these coordinates at that time on that day, was that you? What happened? And they would say, oh, yes, that was us. We did some maintenance. And yes, no, we had, you saying it, you say it was 120 tons an hour. Actually, it was 122 tons. So we had this kind of comparison. But Gazprom was an exception. And most companies are very reluctant when you cut them red-handed. There's a lot of pushback, or a lot of denial, or a lot of reluctance to lift the veil and own up to the release. So this other way, the Stanford study is an independent test, independent exercise, where a few groups, including us, were involved, and we basically were asked to identify releasers. And the conclusion of the exercise, there was a couple of them. Some of it was published in Nature. There's other publications in the pipe, but the results were a full validation of the accuracy, the usefulness of satellite detection. And one of the surprising findings was that the sensitivity of satellites was just as good as aerial surveys. You know, aerial surveys, you run a drone or an aircraft with sensors over a field of oil and gas, for example. That's another way of detecting methane, much more onerous, much more expensive. You can only do it occasionally, and in most of the world, you need the permission of the asset owners to do it. So not quite as, I mean, some constraints there, but the accuracy, the sensitivity used to be finer than that of satellites, but now satellites are basically at the same level of sensitivity. So very competitive in terms of the sensitivity level, but extremely competitive in terms of the cost. You know, very, very cost efficient. And this is something that can be done all the time. So there are, you know, we use as one of our sources is S5P, Sentinel-5P of the European Space Agency. The revisit time is daily. So this is a very, very high frequency.
Now, using satellites, are there any negatives to using satellites? You know, people are complaining about space debris, sustainability in space. What do you think?
I think, you know, this is certainly going to be an issue in the longer run as more and more satellites are being launched. The issue of debris is going to come to the fore. Space war is a risk that we can't ignore. Hopefully, a very low risk, just about the same as, you know, nuclear war, but something nevertheless to think about. Another risk, much more benign, but to keep in mind is as more and more as satellite measurements become more and more openly, willingly adopted, accepted, and leveraged by operators, by governments, by the financial sector, by even NGOs, the public, you name it. This is going to attract more and more actors, both on the hardware side, you know, instrument builders and launchers, and on the downside, on the downstream, the analysis side, the processing and the analysis. So we might see, you know, as you might see more and more groups trying to get a piece of the pie, and there might be some deterioration in the quality of the analysis that's being provided out there. So that's something we have to manage. There will be governance issues about, you know, how can we handle, how can we manage at scale how can we organize international regulations to take advantage, to leverage satellite monitoring, but how can we do it in a way that's non-confrontational, non-litigious? So there's going to be some issues, but the balance is the advantages outweigh the concerns by, you know, orders of magnitude.
Now, let's look into the future. As the technology evolves, what is your prediction for how satellites are going to help with climate change?
I think they're absolutely key. I don't think we can achieve our climate goals without satellites. They have many advantages, you know, accuracy, frequency, coverage, sensitivity, but one of the key advantages beside low cost and cost efficiency, is the independence. No permission is needed. The data are not proprietary. They can be verified. Transparency, verifiability are key to accountability and key to climate action, key to hold emitters accountable, key to establish the basis of trusted carbon market, a trusted market in carbon offsets in forestry projects, for example. They're absolutely fundamental to our climate policies, our climate strategy, our ability to deliver on climate targets. We've seen already the impact of satellites on policy, for example. At COP21, just before we created Kayrros, there was no mention of methane in the Paris Agreement. We knew about the problem, the threat of rising methane concentrations in the atmosphere. We had no idea in detail where methane emissions were coming from. So there was no policy goal of reducing methane at the time for lack of transparency. Since COP21, we've seen this revolution in transparency about methane, and this has really enabled bold policy moves around the world, particularly in the US with the RRA and its methane provisions, with the new EPA regulations on methane, also in the EU with the methane strategy and the plans to put a price on methane on imported methane. But we see also steps being taken around the world. And at COP28 in Dubai, this was a methane COP. There was many agreements, some by countries, some by companies. So tremendous impact. We're going to see more of that, and we're going to see more adoption. We're going to see more use cases developed around satellite detections, and this is going to be across the economy. Operators, consumers of energy, carbon-intensive industries, finance, covering anywhere from hedge funds to insurance companies to banks, and all aspects of the economy will, I think, leverage satellite data in future, and that will help us deliver on the climate goals.
Antoine, it's been very interesting. Thank you for joining me today.
Thanks. I enjoyed it. Thanks very much.